Hi, in today's video I'm going to go over a Brønsted-Lowry acid and base. Now Brønsted-Lowry is one definition of multiple that have been proposed for acids and bases, but it's probably the most commonly used, especially in AP Chem and like Gen Chem college classes. So according to this definition, an acid is a proton donator. So the proton, right, just being an H+. And then a base is a proton acceptor. So if I were to react HBr and NaOH, I would end up with water and NaBr. Right. In this definition, this is the acid and NaOH is the base, because the HBr donates a proton to the hydroxide ion. Right? If I were to write this out, that's HBr, that's NaOH. Now both of them dissolve completely in solution. But what's happening once they're in solution is you have OH minus, and it comes and gets that hydrogen. So it accepts the proton, and HBr donates the proton. Now there are some molecules, the main two being water and ammonia, that can act as an acid or base. And this is called being amphiprotic. It can act as an acid or a base. So water, for example, if it reacts with sodium cyanide, you get HCN and then NaOH. Right? The water donates one proton to the cyanide molecule, Cn-, so it becomes HCN, and then cyanide accepts a hydrogen, so that's why water, in this case, is the acid, and sodium cyanide is the base. Now, a quick note on the sodium in there, it's just a spectator ion. Pretty much anything that is bonded to sodium is going to dissolve in an aqueous solution. So oftentimes bases are going to be attached to a sodium, because that is going to allow them to dissolve in the solution and then be reactive. But the sodium doesn't play a role in the reaction at all. So you could think of this as just being, I'll use it in green so you can see, this is basically just water plus Cn- to give HCN plus OH minus. You can write it like that and just not include the sodium. Now water, like I said, can also act as a base. So if I have water reacting with sulfuric acid, H2SO4, I'm going to get H3O plus and HSO4 minus. So in this case, sulfuric acid is the acid, and water is the base. Now notice here, sometimes you may see H plus written, other times H3O plus. They mean the same thing. They're interchangeable with each other. But H3O plus is closer to what the molecule would look like, because you have a water molecule that accepts another one to get H3O plus. But H plus, H3O plus are interchangeable. Now a few more notes on notation. Every acid-base reaction has a conjugate acid-base pair. So for example, HF plus H2O is in equilibrium with H3O plus and F minus. HF is the acid here, right? It donates the proton to the water, and water then is the base because it accepts the proton. On this other side, though, if the reaction were to go in the reverse direction, so H3O plus F minus to yield HF and H2O, water here would be the acid. So this is called the conjugate acid, and then fluoride ion would be the conjugate base. So notice the anion from the acid becomes the conjugate base, and then the ion that you get from the base becomes the conjugate acid. Right? The easiest way to think of it, though, is just do this reaction in reverse. Which one donates the proton and which one accepts it? Well, F minus accepts the proton that's donated from H3O plus. So that's how you label the conjugate acid and conjugate base. Now, this is an equilibrium, right? Many acid-base reactions will be equilibrium, and the equilibrium is going to favor the side that has the weaker base. So in this case, water versus F minus, the F minus is the weaker base. So the equilibrium is going to favor the right side of the reaction. Now, the stronger the acid, the weaker its conjugate base. So when we say the reaction favors the side with the weaker base, that also means equilibrium favors the side that has the weaker acid too, right? Because the conjugate base is going to be on the same side as the conjugate acid. So the side that has the weaker acid is also going to be the side that's favored. Likewise, the stronger the base, the weaker its conjugate acid. Now, in terms of determining the strength of an acid or a base, right, pKa is a measurement of that has to do with equilibrium. But that's a little bit further down the road with that. The first way to differentiate them is there are 7 strong acids. And strong acid means it dissociates completely in solution. So for these strong acids, there are not going to be any equilibrium arrows because it completely dissociates. So the 7 strong acids, HNO3, H2SO4, so nitric acid, sulfuric acid, then HCl, HBr, HI, HClO3, and HClO4. Those are the 7 strong acids. So anytime you see these acids, you'll have complete dissociation and there will not be equilibrium arrows. Weak acids partially dissociate in solution, and that means there will be equilibrium arrows. So for weak acids, some common ones you may see include, HF, or acetic acid, H2, HC2, H3O2, HNO2, nitric acid. You could also have phosphoric acid, H3PO4. That's another common weak acid. But basically any acid outside of those 7 strong ones is a weak acid. And these ones will have the equilibrium arrows. So an example would be HC2H3O2, so acetic acid reacting with water to give you acetate ion and hydronium ion, H3O+. And then lastly, you'll have some molecules with hydrogens are non-acidic, or their acidity is negligible. So think here, methane, CH4, hydrogen gas, H2. They have hydrogens, but they are negligibly acidic.